Okay, we'll try that again. So I'm Mike Douglas, and this is the CMSA New Technologies in Mathematics seminar. And today we're delighted to have Katherine Collins from the University of Cambridge, and co-speaking virtually will be Jiang, also from the University of Cambridge. And they will tell us about evaluating language models for mathematics through interaction.
Yep. Okay, we'll share screen. Works. Great. Okay. Hopefully everyone can hear me. Thank you so much for the kind introduction, Mike, and for inviting myself and Albert to speak today. I'm excited to talk about evaluating language models for mathematics through interactions, which is a paper that we kind of released a working version on online recently, and it's currently under review. And this work is with a fantastic array of collaborators. I think one thing that I'm personally most proud of is that we have a really wide-ranging interdisciplinary team of machine learning AI folks with mathematicians, cognitive scientists, human-computer interaction researchers. I think that that kind of really captures a lot of the heart of the work that we were trying to do, which is bringing together different folks from different backgrounds to better understand these systems that are kind of poised to transform many aspects of our daily lives and help us push the boundaries of science and mathematics. And again, a big shout out to Albert, who is currently virtual in Cambridge and is going to be joining the discussion later on. And if any questions emerge during the talk, feel free to just chime in. I can either answer them or Albert can help answer them online. So to kind of start, I just want to reflect on how amazing, in many ways, language models actually are, that we now have systems that we can actually converse with in natural language, that we can kind of co-write code, co-write books, help us better learn. We were just having great chats about LLMs in education, even possibly help us to kind of better make diagnoses or treatment plans. So not necessarily there just yet, but I think that it's really amazing that we have systems that are kind of closer to what we might have imagined from science fiction, something like C-3PO that we can connect with and engage with through kind of the medium of natural language, and help us to better understand, be more productive, and engage in the world. We're kind of approaching designing thought partners that we can now work with in these new mediums. But when we think about designing thought partners or human-machine teams, we really need to know when we can actually trust these systems, have faith in their responses, and in order to be able to use them in various practices. In order to do this, we really need to have a deep understanding of the strengths and weaknesses of these systems, what their capabilities are, when we should trust them, how we should use them effectively and appropriately, which is kind of the term that is coming up in a lot of legislation and different conversations around human-machine teams. So this is really what we wanted to focus on in this work, is kind of help be more creative and bring new methodologies and practices to the ways that we interact or that we evaluate these systems. So I'm going to go through kind of the standard practices, the dominant approaches of evaluating language models, and then touch on kind of what we did in the math space. So to start, many of you might know, but in case you don't, that the common way of evaluating language models is that you have some data set of questions and answers. You then feed that question in through some kind of model, your language model. You get back a generated answer, and then you check whether that answer matches some reference. And you do this for many, many problems from your data set, and you can kind of construct an aggregate score. But this has many, many issues, and it was raised in a really great piece in Science recently by Brian Burnell and colleagues. Brian's also a colleague at Cambridge. Where they highlight kind of the issues that can arise from evaluating these models just based on aggregate scores. And they kind of really push forward and kind of advocate for an approach of evaluating these systems on instance-specific cases and kind of a more granular, fine-grained account and showcasing that rather than just saying, oh, we got 63% performance on some combinatorics problems. So these are two different issues of one that we are evaluating these systems often through static tasks. We have a data set, querying the language model, and just checking responses, and then we're aggregating the results and not giving a fine-grained analysis. And this is what we really tried to do in the work, kind of build a more interactive and dynamic evaluation. And so when we're thinking about actually possibly using these systems alongside humans, we really want to make sure that the evaluation is done in concert with humans, and we can better understand how these systems perform when they're actually interacting through multiple steps with people. And I'll touch on that more of why I personally find that so important in the way that we evaluate these systems. And two, that we really want instance level case studies, especially with domain experts. So say if we're actually evaluating these systems for, say, some aspect of higher level mathematics or mathematics generally, as well as other expert areas, that we really want to make sure that we're doing it with domain experts. Personally, Kevin, my background is more in cognitive science and AI and kind of bleeding more into mathematics, but I'm by no means an expert mathematician. I should not be the one evaluating these systems on higher level mathematics problems. So this is kind of what we tried to do, addressing these two desiderata in the evaluation that we pushed forward. And you might say, then why do we do this actually in informal theorem proving? There's many other domains that we could have done this, and we hopefully will continue to do these kinds of evaluation work in. But we had several reasons. One, that proof assistants have kind of long been a dream, and there's quite a lot of active work already in kind of interactive systems of what happens now that we have these more powerful language models. We really want to make sure that we have a deeper understanding of their strengths and weaknesses before they could be slotted into these kinds of systems. Two, that there's not necessarily a clear notion of correctness and or helpfulness when we're looking at kind of theorem proving systems. And third, that a lot of the AI math results to date have been more in the static benchmark setting, particularly also with kind of earlier stage mathematics problems of, say, looking at elementary mathematics or kind of moving more towards high school. We really wanted to look at this in a higher level setting, yet kind of we might be deploying these tools increasingly in educational contexts, or researchers might be using them in daily practice. So again, we really need to understand how these systems work when actually combined with people. And the other point that quote from Albert is that it's just cool that there's mathematics is so fascinating for many reasons. In particular, close to my heart is that mathematical cognition and how humans can even reason about mathematics and push the boundaries of mathematics, and why mathematics might be so difficult to so many people. I think that is a really interesting kind of reason to study these systems in the math space. And as I'll touch on later, we have a new work led little cover bit with Jiang, who's a great PhD student from MIT, where we try to kind of call for looking to cognitive science in the quest to build AI systems for mathematics. So I'll kind of go through what this talk is going to be, very similar to our paper of kind of these two different prongs that we are trying to address in our evaluation of, one, making interactive dynamic evaluation, and two, doing so in concert with domain experts and kind of building out instance level case studies to kind of generalize or uncover and then hopefully carefully generalize some of the insights to inform future modeling and use of these systems. So we'll kind of map this out. I'm going to go through first our systematic interactive evaluation, then touch on some of our expert case studies, and third, close with some of the takeaways that we've attempted to synthesize through our results, and kind of touch on two concrete directions that both Albert and I are really excited about from our work, as well as kind of other bigger picture looking ahead. And as I mentioned, Albert is going to be joining the discussions. Hopefully we save time at the end for that, and kind of can discuss with you all here as well as online. And again, at any point, feel free to pause to ask questions. So kind of first, I'm going to go into our systematic interactive evaluation that we did. As a reminder, the standard practice, and this is by no means the only way that people evaluate systems. There's certainly a lot of great work that kind of does alternate approaches, but when Albert and I were starting this in particular in March, that this really was the dominant approach, that we wanted to look at kind of interactive evaluation, where instead of just immediately sending the question to a language model and checking back the response, that we actually have a person here who's kind of coming up with their own query and engaging with the language model in multi-step evolving fashion in order to try to solve some task that we might have posed. And then instead of just checking whether or not the response matches some reference answer in the end, that we can actually check correctness and helpfulness. Also, here is said in the background, who I've just alluded to earlier in the talk. I said, so then we had people kind of get correctness and helpfulness. And there, in order to do this kind of work, we actually needed a new kind of software tool in order to do interactive evaluation. We called this CheckMate. So we developed a system that lets you easily interact with any kind of language model or kind of do these sorts of human studies at scale. We designed it to kind of enable both the kind of individual model evaluation as well as cross model. So people could engage, and I'll show some interfaces with a single model through multiple different steps, rate the responses of that model, and then also kind of rate their preference across a suite of different models. And third is that we really designed it to try to be extendable. So extendable, that you could do it on a new range of math problems with new users, and or extend beyond mathematics to other domains. And the way that this is structured is it's a few different interface screens that I'll just walk through. So what we would do is we'd show people some particular theorem that we wanted them to prove. They could then engage here with the model of just typing anything, kind of like a general chatbot. We did some kind of, this was led by Albert, but really great automatic parsing. People could then interact and engage with the model over time. Then when they were done engaging, we asked them to rate for each response that they got back from the model. They could ask any queries that they wanted. They would then rate the degree of helpfulness of the response, as well as the mathematical correctness of the generation. I mean, they did this for each of the steps. And people rated or kind of engaged with 3 different language models. They were blind to what the model was. So we had them use GPT-4 at the time, the latest ChatGPT 3, as well as InstructGPT, one of the earlier GPT models that wasn't optimized for chat at all. And people did not know what model they were engaging with, so we blinded them entirely. And then after they engaged with each of these 3 models, randomly shuffled, we then had them rate their preferences of which model they liked best as a mathematical assistant. And we did this with a range of math students, about 25 different participants from Cambridge, MIT, I think University of Vienna. We kind of sent around a participant survey and ended up collecting over 250 human-machine interactions on problems drawn from ProofWiki, so around undergrad-level mathematics problems. And as I mentioned, we did this for three models, and people were blind to the model. We had a decent range of math topics that were covered as well. And we also released this data set entirely on GitHub, as well as our our kind of interactive evaluation platform. So now to go into some of the, I'll actually just pause briefly. If anyone has any questions on our data that we collected, or the kind of evaluation platform that we built for this interactive chatbot style engagement. Yes. This is a great question. Albert was the one who largely chose the problems from ProofWiki. Albert, if you are on, I don't know if you want to answer that.
Yeah, so I basically use like 2 principles for choosing the problems, although it's like not very principled, but the 2 principles I go for is, first, it's self-contained. So a problem ideally does not involve like it does not ideally involve like 100 other lemmas. And the second is that it's usually like just using relatively simple concepts and definitions from undergraduate level mathematics, and usually like prove some meaningful theorem at the end of it. And that it's available on ProofWiki.
Yeah. Thanks, Albert. Yes. So I'm going to go into, if anyone has any further questions as we go, feel free to stop. But now go into some of the insights that we got from the data that we collected. So first off was kind of somewhat expected of looking at which models were preferred as the mathematical assistant. Again, people were blind to the model, so they didn't know if they were interacting with GPT-4 or one of the earlier versions. And what we saw is that indeed, kind of models that were optimized for chat were preferred, which we might expect, that it was really nice to at least get this back from the results. So walking through what this is, rank 1 means that it was most kind of ranked as most preferred as a math assistant, 3 as least preferred. So we do see that InstructGPT, which is an earlier model, not optimized for chat, was often kind of ranked last, not a great mathematical assistant. I do think it's interesting that we didn't see that GPT-4 wasn't always rated as the top. I don't think we have enough data to really make broad conclusions here. The main note is just that even blind to what model people are interacting with, we are getting kind of sensible patterns back. Where I start to find the most interesting insights from our data is when looking at people's correctness and helpfulness ratings. So what we found is that correctness and helpfulness, again, as expected, are pretty strongly related. So each point here is representing one query that a person had done with the model and their rating of the mathematical correctness and the overall helpfulness of that response back. So higher means more correct, higher means more helpful. There's also no 0 here for correctness because we gave people an option that if the response didn't contain any mathematical related topic, we didn't want that to that should be rated as correct or not. And here we also color by what model people were interacting with. So we see that as expected, there's kind of a strong correlation between the correctness and the helpfulness of responses. What I think is perhaps most interesting is that these can actually diverge, that there's really interesting cases where we see that a response was correct, but not particularly helpful, or incorrect, but deemed helpful. So we've kind of been trying to do a deeper dive of why this is happening. For the incorrect but helpful, this seemed to be that if the model was kind of getting at the structure of the problem and making a kind of general route towards the response to help people kind of get some insight into the problem, that could be deemed helpful. Here, with the correct and not helpful, were especially long verbose responses that people really didn't find that very helpful. As humans often in engagement, it's not really helpful to get a very, very long response back. And this is definitely a weakness of these models. But I think that this is an area that personally I'd be very excited to continue to explore. But a really important question is raised is correct really correct? As I mentioned, that we're having people rate the correctness of these responses, but it's not always obvious if someone actually is able to rate the correctness. So we had participants rate their self-confidence in their ability to solve the problem before they actually started engaging with the model. And what we, or rather Albert, Bill, and Freider, who are all more mathematically trained, found instances where participants who were not confident in their ability to solve the problem actually rated responses as incorrect, or rated responses as correct that were actually incorrect, which I think gets to a real challenge and concern with some of these models that they can write such nice, sweet, natural language responses that it can be easy to miss errors, particularly when no confidence is kind of expressed, or perhaps overconfidence. I would also say that from personally looking at these, it really is very tricky, that there were times that I thought that a response was incorrect, that it actually was correct. It can be really hard to grapple with. And I think that this is a really important takeaway when thinking about using these systems in practice. And we also ask people for kind of free-form responses at the end. And in response to the question, were there times when you didn't know whether the model's generation was correct, and so how'd you handle us? We got a range of interesting responses that are in the paper, but one that I wanted to call out particularly, I realize it's a lot of text, but try to highlight the parts that I think are most interesting. That this participant noted that they were often too lazy to check the model's lengthy responses. I think this is a concern, especially when these systems are generating a lot of text. And that there was one instance that they kind of didn't realize until the very, very end that the model's response had turned out to be incorrect. So I think this just gets to the importance of really nuanced, granular evaluation of these systems. And particularly when we think about kind of deploying them in practice, using them in our daily lives. It's really important to pay attention, as I'll get to kind of at the end. We also had, as I mentioned, let people interact with the models however they wanted. The interesting question of what kinds of queries participants were making in the first place in response to the different proof tasks that we were given them. So these are new results that are in the version 2 of our working paper that we posted fairly recently to archive. What we did is we then went through each of the 261 human AI queries and categorize each of these according to particular buckets of whether they were asking for a definition or just kind of pasting in the original problem and trying to get a response back. And from this, we produced what we call query profiles, kind of signatures of the kinds of queries that people were making. And we looked at this, kind of decomposed the queries people were making based on the step in the interaction. So step one versus the second step in an interaction, as well as based on other aspects of people's expertise who were doing the study. So first, I think one of the interesting findings, and I'll go through two of them on the query profiles, as one is that people's queries change over the course of interaction. So people's queries for the first step that they interact with the model often differ from the second step. So I'll go through what I mean here a bit more. So these are the buckets that Albert, I, and several of our other co-authors had come up with when looking at these, the queries that people were making. I went through. Step 0 is kind of the person's first interaction with the language model on a particular task. Step 1 is the second. The second step, the percent is just the proportion of the total queries for that step aggregated across everyone. What we see is that it's more common in the first step to either ask for a definition or just kind of paste the original question. But then as you get later, say the next step, you might be kind of correcting the AI's output, asking why, asking to clarify, kind of these other kinds of query behaviors. And I think this also gets to one of the reasons that interactive dynamic evaluation is really important, that kind of designers of these systems, I think, should really think about how or try to better understand and learn about how people's queries evolve over time, that it could be that after X interactions with these systems that new queries are emerging, and we want to make sure that the models are actually robust and can handle and generate sensible text for these kinds of queries. But if we're not, first off, if we're not evaluating them in interaction with people, we might not even know what queries are being made. But also if we're only looking at a single step interaction, that the queries could change. This is one angle of the query profiles that we found particularly fascinating. And the second is looking at experience and how that changes people's interactions with these systems. And here, experience is actually the amount of time they've played with AI systems, AI chatbots. Previously, we'd asked people that in the survey as well. And what we see, fascinatingly to me, is that people who interacted with AI systems quite a lot previously had very different behavior than those who had never interacted with a chatbot before. And I think this also gets to kind of some of the AI literacy points that Mike and I were discussing a little bit earlier today, of kind of how do we get people to use these systems appropriately and responsibly, is I think we also need to help educate people of what kinds of prompting behaviors lead to the best performance of these systems. So we can see that people who'd had either kind of extensive or at least regular interaction with chatbots compared to those without were more likely to ask the model for definitions, which the models actually are much better at than just copy and paste the original question all in one go. That the models are often, at least my own experience, not great at just kind of being given a question and having it generate the entire response all in one go. And what we see is that people who have interacted with the systems beforehand seem to have kind of captured that it's better to ask for a definition or some other kind of stepwise question. But I think that there's a lot more research that can go into this kind of work of looking at user queries and their evolution. So again, I think the main takeaway from this part of the talk so far and our results is that if we're to design kind of AI thought partners, systems that will actually work with us, we really need to make sure that we're evaluating these systems in practice with people through multi-step kind of dynamic evaluation. So I'll pause here if anyone has any questions on this part before I go into touching on our case studies.
You're gonna.
Yeah, I guess this is almost a case study, but we then I'll touch on some of the work that Bill, Tim, and some other mathematicians had done, where they kind of did a deep dive on some particular problems with GPT-4.
But what about examples from this set of interactions? Do you have any?
I guess we didn't put any here. We have some in the paper, but we should. Yeah.
I mean, I'm just curious, what a typical interaction would have looked like how many times do they go back and forth?
Great question. Yeah, for the times that they go back and forth, usually people went around 3.5, I think was the number, but up to 12 interactions was the most that someone took on one particular problem. But it was kind of in the lowish.
What's the time frame? Like they're for hours or just 5 minutes or what?
I think 30-ish minutes. There was one challenge that Albert and I have discussed that we'd like to do in a future version of CheckMate 2.0 is that there's latency issues with the model, that when you query GPT in the way that we had the system, it would take a little while to get a response back of a few seconds. That can be kind of painful and annoying to work with. Yeah, so it was a medium number of interactions per problem, but not anything like 30. We limited to 20 interactions, just to be sure that people didn't blow our budget of GPT tokens and engagements.
And they usually did finally solve the problem, or?
So this is where it's a bit, we asked people to stop when they felt that they'd kind of solved the problem. I was talking to Mike earlier that it'd be good if we do a version of this where we actually have students who've never seen the problem before, and then their transcripts are rated by, or kind of graded by a separate grader. Because here was kind of more of a self stop. We have some plots in the paper on when people stopped, that it was sometimes kind of a frustration cycle from what we could tell, that people were trying to correct the model's output or get it to respond to something, and it was just not responding sensibly, and it people then just stopped.
Right. So it's not like, oh, in every case they eventually solved it. Sometimes it just.
Sometimes the model it just got into a sticking point. It's a great question. Yeah. Move on briefly to, and I'm not going to go as much into the individual case studies that each of these mathematicians had done, because I don't think I can do justice to it from just this talk alone, but it's in our paper fully. But what we had here was we worked with 3 amazing folks with mathematical background to kind of gave them access to GPT-4 and said, particularly for Tim, of kind of any problems that you would like to explore with these models, and kind of let them kind of freeform engage with these systems and try to draw different conclusions, and then we kind of released all the interaction traces. But just for some of the takeaways from their case studies, that one, as I alluded to, which we also saw in the more systematic survey, is that these models are actually pretty good at producing definitions. So on the positive, that is good, and they can, similar to that kind of incorrect but helpful, can get somewhat of a scaffold of the problem, which could be valuable. But they seem to over rely on memorized solutions. Tim did a lot of deep dives on this, of kind of looking at just slightly pushing a common problem into a less common space, that you can kind of see the model either sticking with some pattern that might be a more common pattern, or otherwise kind of relying on memorized results. Algebra in the systems, at the time that we were looking, things are moving very rapidly and evolving, and we didn't look at anything with Wolfram Alpha plugins, which helps on many ways to address that problem, but algebra really is a key failing. And I think this also relates to a peculiar behavior that these systems can sometimes seemingly solve very complex math problems, but then fail at other areas that you would expect to be solved. So algebra, certainly at the time we were studying, this was a challenge, as well as kind of complex planning in mathematics, but of course more broadly in LLMs. We had some issues with. And then the last point of verbosity, that these models really tended to generate quite long responses. So these are some of the findings, and we have all their case studies available in the full paper. So I'm just going to close with some of the takeaways that we've drawn across these 2 different modes of evaluation, which we've tried to decompose into 3 different buckets of kind of communities that we think could benefit from looking to some of the aspects of our study. So first, for ML practitioners, we really need our models that can communicate uncertainty to users to avoid these issues that I touched on, as well as kind of improve the conciseness of these models and the concision, and enable better explanation of kind of why a result was discovered, or why a particular response was produced. That was one thing that emerged in some of the queries that people were asking. 2, for kind of people who might use these systems in mathematics in particular, I think really taking a careful look at when these systems might be valuable, noting that we don't want to use these for algebra is especially important, as well as just to pay attention, as I raised, that it can be tricky to tell whether these models are correct or not. So it really is worth doing just a closer look. We have pay attention in the paper quite prominently. I use a lot of exclamation points and try not to use it in academic writing, but this is the one part that we did have an exclamation point in the paper because I think it is really important. And third is that when we think about kind of broadly evaluating LLMs, not just in mathematics, but more generally, that it's important to do so in a way that engages with the people that might use these systems, with domain experts who could give a better insight into these models as capabilities, and even raise new questions that we might ask in the evaluation stage that people who aren't trained in that particular area might not think of. So I think, again, this kind of collaboration is, we found really valuable, and hopefully more people continue to pursue it. And again, kind of really better understanding how to effectively use these systems and to appropriately use these systems. So I just want to close from the takeaways of the talk with another two sets of participant anecdotes in response to the question of, are there cases when you might use these systems to assist you in mathematics that I think are interesting and inspiring for future work to actually meet some of these challenges of one participant, and again, highlighting things that I think are particularly interesting, noting that it might be a complement to classical literature search, a tool to improve their writing, but that at present, this person would be afraid of using it kind of almost as a critical thinking tool, that you don't want to develop incorrect understanding when you're trying to learn about some topic and you're getting not gibberish, but seemingly nicely written text back, but that is not actually true. And here, the kind of this person might use it for an initial pilot study, like similar like to what we were talking about, and also to policy writing, especially if they're non-native speakers. So I think definitely really exciting use cases of these systems, really important if we are to build systems that are thought partners that can help us on some of these tasks, that we want to make sure that we have a deep understanding of where these models can meet those needs and where they might fail through interactive evaluation. So I'm just going to close briefly on two different directions that I and Albert have been excited about. So I said, and then open up to a broader discussion. So one is actually what it really takes to build a human or a superhuman mathematical AI system. And this is work with a range of awesome collaborators of Sed, who's in the back of the room, Adrian and Josh, that we've been trying to think about recently, looking not just to math and AI in order to build better reasoning systems, but also to really take a strong inspiration from cognitive science and look to how we as humans are able to learn mathematics, push the boundaries of mathematics, kind of what helps us unlock those capabilities. And in this paper, we touch on 5 different areas of cognitive science, more position paper that we think people would benefit from looking to further, particularly inspired by our sample efficiency in learning, that it doesn't take 5,000 textbooks for us to learn some concept. We kind of might also spend a lot of time with a particular concept in order to learn it, but we can kind of get by with often a lot less data than these current systems seem to take, that we can form rich concepts and structured representations that we also discussed a little briefly, and that we not only can solve goals that are set for us, but we can actually choose our own goals, invent new problems to discover. And we can do so despite pretty strong kind of limitations that we might have on our cognitive capacities. But I think that there's really an interesting open research question that Seth and I have been discussing on kind of when those resource limitations might be actually an advantage, of whether that forces particular kinds of abstractions, and that we often kind of spontaneously explain or try to seek explanations for what we're learning, and that we communicate with other humans through the text that we write or the kind of talks that we might give, and how that informs our broader mathematical conceptual base. So I also want to give a brief shout out to work that I find particularly exciting in the realm of world models and the ways that we build kind of structured representations that we can simulate from Leo Wang and Gabe Grand and others at MIT and Stanford. Leo is also a great collaborator on the interactive math evaluation work. This also connects to kind of communication and explanation of the ways that we then describe what we know and express what we know to the world. And that touches on another direction that is Albert has been working on, which is to kind of think deeper about the relationship between informal and formal mathematics. That the majority of mathematical data available online is informal. That formal data is much more limited, but as great work that Albert can maybe touch on if interested in the discussion, is that if we want to kind of augment formal math data to then train these systems, that we really need diversity. And I'll let Albert touch on that further, what he means there. But I think that these are two different questions that we've both been excited about. Of one, how we can actually build better mathematical reasoning systems, and also better understand how we can even solve these problems in the first place and pose new problems. And two, kind of thinking more about the data angle, particularly the expression of mathematical knowledge. Yes.
Okay. Informal means human.
Yes, I should clarify, and I'll maybe let Albert. Do you want to respond to that if you can hear?
Yeah, sure. So by informal mathematics, I just mean the everyday mathematics that we actually practice, that we actually write down, including in LaTeX. And by formal mathematics, I mean mathematics that are present in proof assistants, which are mathematical statements and proofs that are grounded in some logical formalism. So that's kind of the difference.
Thanks. Yes. So just to close, these are a few points that we'd be excited to discuss here more broadly of kind of what is or what will be the relationship between mathematicians and these new kinds of tools, what we want that to be, particularly across stages of mathematical or really any kind of development, say in educational contexts, how we can actually build systems that are effective thought partners, that can kind of meet some of those desiderata that we had raised as takeaways from our study, and where we might want to integrate LLMs with other kinds of AI systems that might be more structured, and kind of how human-like we might need these systems to be if we are to use them. Do we want them to be human-like? We need them to be human-like. I think that those are really interesting questions, as well as kind of on these data points of what the trade-off between getting more human data versus synthetic data, as we also touched on, are, as well as kind of expanding beyond language data to say multimodal image data, especially for something areas like geometry. So just to close, I want to say thanks to amazing co-authors that was very fun to do this kind of work with. If you have any questions, you can contact either myself or Albert. Our code and data are available, and we'll also be at NeurIPS if anyone will be there. We've been co-organizing a math AI workshop. Also wanted to raise that said his contact info as well on some of the more cognitive science front. So that's it. I'll leave the discussion question up as well. But pretty good.
So we'll go to questions, but we have a little more time. Katie, how hard would it be just to take the paper and put up a trace of an interaction with ChatGPT? Is that on your screen? Is that something?
Yes. Let me. Yeah, I can. Let me stop my share. Is there a particular one that you'd wanted to see? Okay. Oh yeah. Let me share my screen. Albert, do you have a favorite of the case studies from Tim? Let me see here. Okay, yeah. Yeah. And then this is also to oh yeah, okay. Oops. And then also as a bigger small, like
Yeah.
Oh, I see. Okay, yeah. I don't know what I was doing. Okay. Yeah. And I also wanted to raise that these kinds of queries are a bit different than what we've done in part one of the systematic interactive evaluation, that there we were kind of telling someone this is the problem that you can interact with the model to try to solve. Here with Tim's, it was more he could kind of choose whatever he wanted to play with the model on. And then this is his summary of the interactions, but then later in the paper, it's the whole actual interaction trace.
Okay, so in this example, I looked at it earlier today. So you can see the question and give us five prime numbers that the first element is actually cardinality of the set. And this one it aces. And then he asked this interesting question. If you scroll up a little bit, why does it not give the more obvious answer of the first five prime instead of what it actually given? And he speculates that these are an arithmetic regression, which presumably appears a lot in the training data. Yes, and it's evidence that it's using off-the-shelf examples in his phrase. It just likes to blow stuff with its data. So then there's another.
Yeah.
Yeah, he changes the question. Can you find such a similar thing where the cardinality is at least 6? Okay, and this one is screwed up and has trouble. He has trouble, I believe he can't get it to actually understand the question.
Yeah, even after the error is pointed out.
Yeah. So it would have to move on to immediately set of 7 elements to satisfy the conditions, and this is kind of too hard for it to conceive of. If you can appeal some way to the stochastic view. So anyways, there's quite a few evaluations like that through the paper. So it's kind of finally getting what it's doing.
Yeah.
Yeah, I think just as a another comment to this particular example is just that we see a lot of language models that are actually quite stubborn. They might be really apologetic and they say, oh, apologize for my mistake, and I realized I've done something wrong, and they try to correct it, but they're actually quite stubbornly sticking to their original opinion. And you also see this when you're asking a language model, like, can you give me an answer to some certain question? And it will be really bad if the model just gives the final answer straight away, because then it won't really reason about how to get the correct answer, but it will try to justify the answer it just gave, like it just gave, like just in one single step. So like that's kind of the really bad like domain of like how you want your language model to reason. You ideally you want it to have a long chain of thought and really go over its reasoning process before giving the final answer. Just as a like additional side note to this.
Okay, more questions, audience here, anybody?
So do you have any information why like those language models are bad at certain categories of problems? Like why they're bad at algebra? Do they have any mistakes?
I think with algebra, it's also whether the systems even can kind of what transformers are capable of. I know that there's been some work from University of Washington also, and I don't know if the Apple hypothesis connects to that as well, of how these systems, whether they actually can compute what the operations needed for basic algebra. So I think that might be one angle. The second is that I also do wonder how much just the data that is available online, as well as we were also briefly discussing this of kind of the curriculums that might be needed to learn that with humans, you go through some development usually of simpler concepts. You make sure you master them ideally before then moving on to more complex problems. And at least the way that GPT-4, to my knowledge, might have been trained, it was not necessarily through that kind of throw everything at it at once. Those are two questions. Yeah.
Sorry to add to the answer. There's another possible issue with the tokenizers. This is in particular to do with arithmetics. So the way these language models work is with text is that they will try to first split all the text into individual tokens, and for I think quite a while people have been using tokenizers that sort of split a single number into like irregular shaped tokens. So if you have a number like 1, 2, 3, 4, 5, 6, it might split it into like 1, 2, 3 is one token, 4, 5 is a token, and 6 is a token. So that obviously limits the arithmetic abilities of these language models. I think for the newer generation of language models, now they tend to use like single digit tokenization, which somewhat alleviates the problem, but does not solve it completely.
I'll make some comments too, because this has been studied up there now. I mean, the first comment is that it's amazing that it can do any algebra, because it's just this amazing generalization beyond predicting the next word. And so that's kind of more the thing to explain. And then people have been studying this systematically, especially for decimal arithmetic, where you have broken the numbers down into single digits, and you just give it the training set. It's just a ab initio transformer trained on a data set of addition problems, multiplication problems, and so forth. And if you just give it that straight, that's actually quite hard for the transformer. And then it really can't do it very well. And then there are many kind of little technical tricks after which it can do addition, and especially what people talk about is length generalization, where you train it on examples up to some number of digits, and can it somehow generalize to examples with more digits. And there's a recent paper from a group at Apple that claims to get this to work. Okay, and it's again, it's a little surprising it would go beyond, but if you make the problem easy enough, so in that particular case, you start with the units digit, because obviously when you're adding, you first produce the units digit using the standard algorithm and so forth, and you tell it explicit positions of digits and so forth, and then it can do it. So it's kind of it's saying something about the nature of both what the transformer can represent and what the transformer can learn, and it's really very open at the moment whether how you could train it, whether it could do general algebra, whether it could do general verification of logical arguments, and but I think the starting point should be to no, it's not going to do it unless the procedures and possibly the architecture are improved in some way, and it's open. Is there some sufficient set of improvements really to get a model like GPT to reliably do algebra? It's conceivable. I mean, the more straight, if you're really interested in a practical model, is probably better to integrate a tool to do algebra.
And I think Wolfram Alpha has gotten better when combining
The
it.
calculator.
Yeah, right. I mean,
Yeah.
it's not the thing that people are the best at either.
Yeah, that's true. That's true. Yeah. Yes.
Did you do any controls where you have a person in the same kind of problem and not the?
No, but we should do that, and that is in our hope for the kind of a future version if we did this with actual students that are trying to then have never seen the problem. Some of the people who've done these problems were even higher level mathematicians. But no, we haven't done that, and that'd be very good of seeing. What we'd like to do is then rate, kind of have a report graded that or proof graded by a student who had access to the model versus not access to the model, and then see how things are.
You have a guess. Is the model going to help the student or hurt the student? On average?
Great question. I would say, I would think help, especially if the student was, say, asking it for definitions if they got really stuck on a problem. I think on average you'd see help, but I think there'd be some cases where the student got wildly thrown off.
Take it for granted, because I've really seen talks where it's like they develop this complicated pedagogical computer system, and then they do the rigorous test and it hurts.
Okay. I my guess would be that it would help, but I don't know.
There's a third control. I forget. I'm not sure you mentioned of the students doing the problem and the second person is simulating the GPT.
We also discussed that of having a human. So yeah, human alone, human model. Yeah. Good point. And I think then human made it Google or something would be another one. That's a great question.
More questions? Okay, let's see. This is, I definitely recommend people to read the paper because it has, as I said, it's kind of illuminating examples.
It's quite long, but it's mostly long because of the interaction traces that are at the end of the paper. There's about 50 pages of just the full like traces of Tim, Bill, and Wenda interacting with models.
Okay, well, if there are not more questions, then well, let's thank Katie.
Thank you.
Well presented piece of work. So this is the last of our seminars for this semester, and we'll start up again on January 24th with Heather Macbeth, who will tell us about the developments with the Lean Theorem Improver and the Lean Math Web. So everybody, thanks for joining us. Have a great holiday season, and hope to see you again in January.
Thanks. Thank you.